Hello everyone. Today let us discuss about the Grand Canonical Ensemble, which is a sort of a little bit more complexity added to the canonical system that we discussed. And in this ensemble system we are going to see what are the differences it has in comparison with the canonical system. So let's start. So now a grand canonical system. Okay, so grand canonical system. So what is this? So this is a system which is in equilibrium between the not between, so or with the surrounding, okay, or the reservoir. A system in equilibrium let's see, with the surrounding. Okay, so let us talk a little bit more about what kind of surrounding we're dealing with. So this surrounding here is our standard reservoir, that is a reservoir with this is a reservoir which has which in the earlier case of canonical, the reservoir was only about energy reservoir, right? So we it allowed exchange of energy only. But now in this case, this reservoir is both particle and energy. Okay, so that means it allows exchange of energy as well as particle between the system and the surroundings. So let's just discuss. So imagine that we have this green shaded region. Let's imagine this to be our surrounding. So let's call this no, let us just use the word reservoir. Okay, so let's call this as the reservoir. Okay, so let us name this reservoir by A dash. Okay, and also let us consider a system where we allow to have this small system in contact with the reservoir. Let's call this system A. Okay, this is the system and let's denote it by A. Okay, so we have a system called A dash, which is nothing but the reservoir, as well as a system which is designated as A, and this in fact is the system that we're interested about. Okay, so now as we just stated in the beginning, this system is allowed to have exchange of energy or heat with the surrounding. Also it allows to have exchange of matter, okay, or in other words you can call it as particle. Okay, so it allows to have exchange of both energy as well as particle between the system and the surroundings. So this is the kind of system that we are dealing with. Okay, and for simplicity, or for to make life easy, we will consider a system having a fixed volume. Okay, this system is having a fixed volume. Okay, So this is the thing that we have to understand. So what is the summary? So we have a system A which is in contact with the surrounding, and we allow exchange of heat as well as matter between the system and the surrounding. So this kind of freedom of exchange of both energy and matter, how that will affect our affect the nature of the probability to find the system to be found in a particular state. So that is our standard question that we are dealing with. So let me just write down. So our interest, okay, our question, big question here as usual is the what is the probability that the system is found in a state denoted by R. Okay, so this is our big question. Okay, so now let's move ahead and try to be a little bit more specific. So let me just write down a few things. So our system, okay, so this is a system A is having fixed volume. Okay, let me just write down a few facts. Okay, fixed volume V, and which is in contact with reservoir A dash. Okay, so what is important to note here is, so let us just assume that so let n is the number of particles in the system A, and E is the energy of the system. Okay, so what we have to note is that both N and E are not fixed in this case, right? In the earlier case of canonical ensemble, if you remember, right, in canonical N is fixed, okay, E not fixed. Okay, this is what we had in canonical, but here in grand canonical both N and E are not fixed. Okay, but what is fixed, okay, is the say total energy of the system as well as the total number of the system. So let's just call for the reservoir E naught to be the energy of the reservoir. Likewise, let's denote E dash. Sorry, E dash. Okay. E dash is the energy of the reservoir, and N dash is the number of particles in the reservoir. Okay, so what is now fixed is, say, conserved quantity. Okay, so what is conserved is the following: the total energy E plus E dash equal to, let's call this E naught, which is total energy, okay, is constant, as well as the number of particles, the total number of particles, n plus n dash equal to, let's call this n naught, okay, which is also constant. So you see, in this, the total number of energy as well as the total number of particles are fixed, okay, but for the individual system, like the system A, both energy as well as the number of particle is not fixed, okay. So let's call this set of equations to be, say, equation number 1, okay. So what we have to understand is reservoir normally is a very large system. So since the reservoir, okay, is much larger than the system, the above relations are in equation 1, so n plus n dash equal to n naught, and E plus E dash equal to E naught. We can write as follows, okay, is 1 minus n dash by n naught, which is much less than 1. Also, similarly for the energy, we can write E by E naught to be 1 minus E dash by E naught, okay, which is much less than 1. Fine. So now let us assume that is omega dash E dash and dash is the number of microstates accessible to the reservoir A dash, okay, and when this is when the reservoir has n dash particles and has energy in the range near E dash, okay, this is what we have to remember, right. So now big question is now let us come back to the question of probability. So what is the probability, right? So the probability of system A being found in a particular state, is let us denote it by, say, P of R having energy E of R, and the number state N of R is now directly proportional to this total number of microstates of the reservoir, okay, E dash and dash, okay, which can be written as omega dash E naught minus E R N R, okay. So which can be written as omega dash, okay, E naught and N naught, approximately. So this is due as a consequence of this, okay, this let me call, okay, this was our equation 1. So we have now see that the probability is proportional to the total number of microstates accessible to A dash. The underlying idea is that the system A, you see, is in principle a very tiny fraction, can be considered as a very tiny fraction of the bigger system, which is represented by the reservoir as well as some reservoir and the system together. Okay, so under this assumption, the energy as well as the number of particles that the system has is a very tiny fraction. Okay, it hardly makes any difference to the reservoir if there is a change of energy as well as number of particles in the system. So that is why the probability here is assumed to be directly dependent on the number of microstates accessible for the reservoir. Okay, now let us do some simplification. So let us try to enumerate this omega dash. Okay, as we noted in the last lecture, normally the number of microstates omega is an extremely large number. Okay, so we have to take log of this omega and then do Taylor expansion about the mean, or sorry, total energy. Okay, so now let's do that. So log of omega dash, okay, which is E naught minus ER, okay, and N naught minus NR, okay, which we just saw that can be written as log of omega dash E naught N naught, okay, and minus del log omega dash by del E dash E dash equal to E0 minus N R, okay, and dash equal to N0. Okay, so what we have done is we have taken log of omega dash and perform Taylor expansion. Okay, now these terms here, okay, we know that since beta is defined as del log of omega by del E and alpha is denoted or defined as del log omega by del N. Okay, so whatever the expression we have here, okay, so this here is beta and this here is alpha. Okay, so we can take antilog and then we have this, or we simply rewrite as follows: E naught minus ER N naught minus NR, okay, is equal to omega dash N naught e to the minus beta ER minus alpha and r. Okay, you could use different subscript r and s to denote the states, but I have just used the same state r. Okay, but in principle it's not restricted to same symbol. Okay, you can use different r or s. Okay, so therefore our probability, okay, probability p of r to be found in the particular energy state defined by er and the number in r of the system is now proportional to e to the minus beta er minus alpha nr. You see, now we have this additional term of alpha nr appearing in the Boltzmann factor for allowing the number of particles to vary, or for allowing the system to exchange energy between the system and surrounding. Okay,